to Physics video lecture, Physics 203 video lecture 17. So we're moving on into a new topic, or an older topic looked at in a new way. So we're still talking about Hamiltonian systems, but we're going to return to the principle of least action, and we have some beginning of some extensive formal developments. So Hamiltonian systems, principle of least action once again. So that's actually how we derived the Lagrangian equations. Principle of least action revisited, for example. You could call it that. So the principle of least action was this, that the variation of this integral with fixed boundaries, T1 to T2, for the Lagrangian kinetic minus potential energy, okay? The variation of that vanishing meant that we had the Euler-Lagrange equations. So dl dqi dot minus partial qi equals 0. Okay. So that's what we had. This was the principle of least action, that the action S is equal to T1 to T2 L dt. Okay. Is the action. So that was the principle of least action. And what we're going to do is extend this now. So this was fixed boundaries, fixed upper and lower boundary. So our next development is to imagine that the action is a function of the upper boundary. Okay. Suppose S equals integral L dt, a little prime there, but now the upper boundary is no longer fixed, i.e. upper bound is no longer considered to be fixed. Okay, so we have to see what that means. See, what we had prior to this, we had a mechanical system, and it was represented, one point in configuration space corresponding to T sub 1, and then there's the motion of the system, point in configuration space corresponding to T sub 2. Okay. And these points were fixed, and what the variation meant, so what this operation here did was to keep the endpoint fixed and to vary this. Okay. Use another color, it's the famous picture. And then we had a necessary condition that this actually be a minimum. When we calculated the action along the red path, it was always greater. Okay, so we had a minimum or an extreme. So now we imagine we have these two points, T1, and this time we'll call it T. Okay, mechanical system ending up there, but this end now is open-ended. Okay, so we're thinking that the system can keep going. Okay. But it's not as though we don't already have this, so let's go ahead and develop this variation. So previously, now upper boundary is, I'll just put in scare quotes, is open. Okay. So this formal operation I'll do like this now. So we have d integral L dt, doesn't matter t prime, okay, is integral dl dq dt plus dl dq dot dt. Okay, just formally here. And we know we had that integration by parts. So this is just a shorthand for the calculation we've done in the past. So we have that first one, dl dq dq, and the second one, we do an integration by parts, dl dq dot dq from the upper and lower bound, and then minus integral dl q dot, not so fast, d dt dl dq dot dq dt. Okay, so I'll put some bounds in here. Upper bound is t, so we'll go ahead and say t0 to t. Okay. T0 as before, T0 to T, T0 to T. Now, the first time around, since we had, that's an equal sign, since we had the fixed upper bounds and lower bound, we required that this del Q vanish at the top and bottom, and we got rid of this term, okay? And we retained these two. So we're going to write it this way. We have, there's room here. So yeah, keep going. We've got equals dl dq minus d over dt dl dq dot, and then common there, the del q dt t0 to t plus dl dq dot del q t0 to t. Okay. Okay, I'm going to erase this and then I'll point some things out. Okay, so here's what we have. This is the variation of S, right? Integral L dt. We've ended up down here, so just to make sure, put a box around here. So we have a red box. There we go. So this is the one we're focusing on right now. And here's what we have. This expression is where we obtain the Euler-Lagrange equations from. You see them here in the parentheses. If this integral, if this first part vanishes, then we get the Euler-Lagrange equations. Well, we're going to retain that because we already know these are the true equations of mechanics. So that's not going to change. Whether or not the upper bound is open or not, we're going to go ahead and retain the Euler-Lagrange equations. So from this part, you know, we don't have to redo the fundamental lemma of the variational calculus or anything. This one gives us dl dq minus ddt dl dq dot equals 0. Okay, so that much we know. But now, since we are treating this as a function of the upper bound, we're no longer going to say that this expression here vanishes. Okay. In other words, we're going to say dq, the variation, vanishes at the lower bound, but at the upper bound it does not vanish. Okay. It's now some function, so we have that, and I'll write and again, this is simply because mechanics works, and this was mechanics. I usually write it in the opposite order. Okay, you recognize that it's the same Euler-Lagrange equation. So now, and by the way, since those are 0, this whole thing vanishes again. So what we now have is equal to dl dq dot LQ, comma, because del Q at T0 is equal to 0. So it's understood that that is with respect to the upper bound T. Now, this we recognize, since we were talking about Hamiltonian mechanics as well, this of course is the generalized momentum. And when we go from Lagrangian to Hamiltonian mechanics, this is the momentum, right? So we can say ds is equal to P del Q, and therefore well, not so fast. Okay, let's just hold on to this. So now what we want to do, consider S as a function of the coordinates and the time, comma, function of the coordinates and the time, namely this upper bound, time was associated with some coordinates. Okay, you have Q of T, you have T corresponding to the coordinates. Okay. If that's the case, then from this expression star here, we have ds dq is going to be equal to P. And this was just a shorthand version for the multivariable formulation of this. Right, I just wrote one out explicitly. So generally, ds dqi is equal to pi. Okay. So that's an important relation. Furthermore, we put this all on one board. Furthermore, if we have ds and take the total differential of something, of a function of the coordinates in time like that, then we would have sum over ds dqi plus partial s with respect to t dt. So ds equals sum over p sub I dqi, and then outside of the summation we've got the ds dt dt. So again, you can see I'm getting the same thing. If I now take partial s with respect to any particular q sub I get the corresponding p sub I there. Okay. Okay, we keep going with this. continuing, we can write the following. Since S equals integral L dt, and t is the upper bound there, we immediately have ds dt, the total time derivative, just by the fundamental theorem of calculus, is equal to L. Because that's the upper bound in the time, so you get ds dt equals L, and from this double star, ds dt is equal to sum of, complete time derivative, actually from this one up here, or this one, but let's go back to the top there. Same thing. We get ds dq sub I q sub I dot plus ds dt, outside of the sum. Now the ds dq sub I, that's p sub I sub I q sub I dot, and then outside here plus ds dt is equal to, got the L there, L. So now let's look at this here. I'll probably work up on top because I got the room right there. But I'll write this here. Recall H is equal to the sum of P sub I Q sub I dot minus L. So what do we have here? P sub I Q sub I dot is equal to H plus L. So what we end up with here is H plus L plus ds dt is equal to L. These go away on each side, and now we have the following very interesting relation. ds dt plus H equals 0. So we've arrived at, as I'll show you in a few minutes, we've arrived at a new partial differential equation for mechanics, or a new fundamental relation for mechanics, and I'll show you in a moment. This is actually a partial differential equation. It's all up here on the board, actually. And what that's going to mean is that this S has now taken on a new significance, right? Originally, in this form with the fixed boundaries, it just seemed to be a device. Right? It was an object whose minimization gave us the equations of motion. Okay. But here it's now it's actually a mathematical object that we calculate in its own right. Okay. So we never wanted to find out what S is. We always just wrote down its definition and obtained the differential equations. This time we're actually going to move on into finding out what the action is. Okay. So there's a little bit of extra development here. This is on the board already. So this whole development has led to that differential equation up there in the box, and we have to see, look at it a little more closely. Okay, I can erase all of this stuff. And in fact, I'll kind of put down our results now so we just can focus on those. other words, summarizing what we've got now, we have nothing like a little numbered list. So S integral L dt is a function of the upper bound, and that is to say, function of the coordinates at the upper bound of our mechanical system. Function of the upper bound, no longer just some object to be minimized. So S in that sense is a function of the coordinates, Q1 to Qn, and the time. And then we have E sub I ds dq sub I that we found, right, that relation. And the last thing is our equation up there, ds dt plus h equals 0. We'll leave it that way, plus h equals 0. So you can combine these things here to look at this new equation in the following sense. We can have, for h equals h of q1 to qn, p1 to pn t. Remember, we're doing Hamiltonian mechanics here, even though we went back to the action in Lagrange. So for h to be given in this form, we have ds q1 to qn and t partial with respect to time is equal to h q1 qn. Okay, so far so good. Now p1 to pn, we can put this, we can substitute this in. So p sub I is ds dq sub I. So here we have ds dq sub 1 all the way to ds dq sub n. That's for the p1 to pn, and t equals 0. Okay, so this has been written out with all the arguments in place. So this is a partial differential equation. Okay. It's a partial differential equation. And so we can easily write it down. We could actually write this down for all of our Hamiltonians that we already know about. Because where we had p, we would put ds dq in there, and then you just have this relation between derivatives, between partial derivatives that has to be solved. So this is a partial differential equation. And the interesting thing is we can write it down, but we don't yet know what it means mechanically. So we're not going to launch into its solution right away, but I will say right now it's called the Hamilton-Jacobi equation. And one of our goals is in the next few weeks to make our way to being able to solve the Hamilton-Jacobi equation and see its relationship to mechanics. Hamilton-Jacobi equation. It'll be a slightly different approach to solving mechanics problems, but it will be the most general one. And what's going to happen, we're going to have to work our way up through a couple more subject topics until we find out what the relation of this is to the motion of the mechanical system. In other words, if we were to solve this thing, yeah, let me mention that. If we were to solve it, the result would be that we know what S of Q is, okay? The function S of Q is unknown in this PDE. We would find out what S of Q is, and we would then from S of Q be able to find out what the momenta are, but we don't yet know what the relation is to the motion of the system, which is the Q of T. So I'm going to put that in words here. And then I'll write down a little bit more, then we'll move on from this. So now the Jacobi equation. So the solution because this is what you literally start out with. You've got a Hamiltonian system, you write down it's Hamiltonian, you go ahead and, before I even talk about the solution, let's just give an example right now so that we're not left hanging in the air. Example would be projectile motion. So projectile motion in 2 dimensions. We could do it in 3 dimensions, but we do projectile motion in 2 dimensions. And let's remind ourselves, I can actually cut to the chase on this one. So the Hamiltonian for projectile motion would be px squared over 2m plus py squared over 2m plus mgy. And then I'm saying the y direction is up, x, y, you launch something at an angle theta, the whole projectile motion business. There's its Hamiltonian. And the Hamilton-Jacobi equation, would then be ds of x, y, and t dt is, I see I put a minus. Catching our mistakes in real time. This is supposed to be a plus sign, plus h equals 0. So we would have x, y, and z dt plus this h equals 0. But now what is this h? We would have 1 over 2m, and then the piece of x is the ds dx. That would be squared. And we'd have 1 over 2m ds dy squared. And we'd have plus mgy equals 0. And s is, function of x, y, and t, same here and same here. So good, we could write that down, and we just did. But if we were, and then we have to learn some techniques of partial differential equations. This is a slightly different form than we learn in other subjects. But good, we learned that, find what S is, but we don't yet know its relation to the motion. So I'm just going to write that down to complete this little section. So there's an example. So the solution, now I'll complete that sentence I was writing. The solution to the Hamilton-Jacobi equation is S of Q1 QNT, where we do know that P sub I is equal to PS and Q sub I, but we do not yet know how to extract the motion. Question. How to use S to obtain Q sub I of T. Okay. Because this of course is the goal of mechanics. How do you get Q sub I of T? Q of T, the motion, greatest degree of freedom. And at this stage of the game, we don't yet know how to do that, so we have to do some other developments that will eventually get us there. Okay, that's pretty good. Yeah, I should point out this formalism is the one with which we can make contact with quantum mechanics. And so that's actually what we're steering towards. But along the way, we're going to learn the techniques of Hamilton-Jacobi theory. Okay, so we'll learn the techniques of using this equation this equation right here, the general form, to find the solution to a mechanical problem. And then the further development will actually lead to Schrödinger's equation at some point. And we have enough time to do that, so I'm not too worried. But that's one of the major goals of the semester, is to go through with this entire theory here, up until we get to the equations of quantum mechanics. Okay. So, where does that leave us here? Before that, we're going to do something called the principle of Mobertuise. So I will erase this now. So the next section, we're going to use some of this formalism and get another principle of classical mechanics called the principle of Mobertuise. So we'll use the formalism up to here, but not that differential equation. That comes later, but the stuff I had right up here we're going to use. Mobertuise was Euler's boss at the court of Frederick the Great back in the 18th century. And he came up with some of these variational principles in a really vague way. Euler did all the work, but he was so generous he let Mobertuise get some credit for it, even though Euler was the mathematics behind it all. So, principle of Mobertuise. And we'll build on what we had just derived. Principle of Mobertuise. Okay. And we're going to use it, so Hamilton's principle which was also the least action principle, kind of use those interchangeably, that gave us the motion of the mechanical system. So motion of the system. Now Mobertuise principle is going to give us the trajectory. So suppose you don't need to know the motion, which is, say, the full time dependence, but you just want the trajectory. Then Mobertuise principle will do that. Mobertuise to get the trajectory. So it's a variation on the principle of least action. And we already did a problem where we just obtained the trajectory, namely when we did the Kepler problem, we didn't take it all the way through to the time dependence. We actually veered off a bit and we ended up with the trajectory, namely the elliptical path of the orbits. Okay. So that'll be a really nice example for Mobertuise principle once we have it. Okay, so we have to get started on this. So we're going to assume we have conserved energy, so H of Q and P, it's not going to have an explicit time dependence. H of Q and P equals E is constant. Okay. And now we have this from the previous board. It's still up there. It is not. We have ds equals minus h dt. Okay, that's just the form of that equation split up. Okay, ds dt is equal to minus h, so these del's are variations minus h dt. That means del s plus e del t is equal to 0. And now under here we're going to fill in what we mean by this, okay, with the momentum. So this again here is going to be that sum actually, let's do it this way. We already have the piece of I right there, so dq sub I. And then we have the minus h dt. So if we integrate this, we have integral sum over p sub I dq sub I minus e t minus t0. So imagine we're integrating this, but the h is equal to the e because it's constant, integrated over time. It's a constant times t minus t0. Here we're along the actual path of the mechanical system, and S is implicitly a function of Q's. So we can bring this to the other side, S plus E t minus t0, and do I have an upper bound there? No, that's good. Equals sum over P sub I dq sub I. And this we're going to name S sub 0 the restricted action, okay, or the abbreviated action. The abbreviated action. And this will get us our new principle here. So let's go ahead and put a box around this. So the variation of S0 equals 0 because we have this right here, right? This is ds is minus edt, so ds minus edt plus edt equals 0. So ds0 is equal to 0, and this is our new principle. V sub I dq sub I is equal to 0. Now we have to turn this into something we can calculate with, but this would be the general form of Mobertuise principle. Not yet to calculate with, but this is the quantity whose variation is going to vanish. Okay, and I'm not specifying any boundaries or anything right now yet. Okay, this is very general still, just off of these expressions. So now we have to get some content for that, turn it into something we can calculate with. And in essence, we have to get some expressions for these dq sub i's. So here's what we're going to do next. All right, here's what we'll have the problematic. Right now we have p sub I, el, dq sub I dot. It's a function of the q's and the dl and the dq dt's. Okay. So that's what our p sub i's are. And our energy, if we were to write it out, right, we're back in Lagrange and Hamiltonian mechanics, if we were to write the energy out, it would be a function of the coordinates. Let me write this. Would be E of the coordinates and the velocities as well. So what we have to do in this whole expression, we have to eliminate the times. Eliminate t. That's our task. And okay. So these things implicitly have q's and the q dots in them, okay? We have to get this expression without any t's or dt's inside, without any dt's from those derivatives, in order to actually just have functions of the coordinates. So that's the goal. And it's not that involved. Let's see how much time we have here. Oh, I may set this up next time. Let's see. We got this. Here's what we're going to do. So E. First, we're going to go back to the formulation we had in our Lagrangian, and that was 1/2 double sum ij aij of q. In fact, I'm just going to write aij of q vector. So all the coordinates qi dot qj dot plus u, which is a function of just the coordinates. So what we have here is 2 times e minus u is equal to this double sum over I and j, aij q, and then we can write dqi dqj, got a dt and a dt. So what we're going to do is solve for the dt in this expression here. Literally solve for the dt. will be one ingredient here. So dt, just by cross multiplying, okay, dt and taking the square root, so we have 2e minus u, other way around. You can have the double sum I, j, aij of q, dqj divided by the 2 e minus u. Okay, so let's hold on to this. Where does this dt go? We have to get an expression for the piece of I. So the sum over the piece of I so far, so good. So now go back to L, which was the 1/2 double sum aij q qi dot qj dot minus u q. So we want to get the piece of, we'll use k. So piece of k is equal to dl q sub k dot. We'll have the 1/2. Actually, this is something we've done before. I and j. aij of q. So we've got a qi dot delta jk plus delta ik qj dot, and remember that collapsed those sums both equivalently. So the first one, when j is equal to k, 1/2 sum over I, j is equal to k, aik qi dot, and the second one, when I is equal to k, so sum over j, akj qj dot. Symmetry of the matrix aik means that you can just take one of these, get rid of the 1/2 sign, sum over akj qj dot. Okay. Summed over j, and this is p sub k. So what we're going to do with this is make this integral sum over p sub I dqi, except we're going to use k instead of I, since I have the k right here. Okay, gotta keep track of our ingredients. This one we need. This one we need. So the 3 red boxes, good. So now, sum over, so integral sum over p sub k dqk. K is equal to integral sum over k, and then the piece of k is sum over j akj d qj dt, and then dqk. Okay, different colors. How about that? Now watch this. So we've got an integral over that double sum. We have a single dt right here, and that's where this thing comes in. So this one I'm going to write pretty large. Equals integral. We've got a double sum. A, K, J, D, Q. I'm going to go ahead and reverse the order. DQK, DQJ. I've got a single dt in the denominator, and that dt is this one right here. Okay. And oh, this dt, by the way, it's been erased, but this was under a square root. So make sure you come back and see where that square root was. I don't have it up there anymore, do I? It was definitely under a square root, because I had dt squared, right? Under square root. So this is pretty amazing. Double sum A, K, J, D, Q, K, D, Q, J. And the denominator of the denominator, we come up here with a 2 times E minus U. And now we just have to simplify. Equals integral. Notice we cancel. This one is the entire expression, this one's the square root, so we're left with a square root. And I'll put everything under the square root. We've got 2 E minus U double sum A, K, J, sum over K and J, D, Q, J, just keep the order nice, D, Q, K. Everything under the square root. So this is our S sub 0. This is our S sub 0. This is our abbreviated action. We're not quite ready to calculate with it, but we're close. By the way, these AKs, we haven't seen them for a while. They're from our general Lagrangian, general form of the Lagrangian, right? This was the kinetic energy, so make sure you realize that. That's what that AKJ matrix is. Okay, so having done that, and yeah, this trick with the dt being all of these things, that's pretty amazing. We'll take it. I didn't make it up, but it's pretty amazing. Okay, so this is the abbreviated action. And to render it useful for calculations, let's see how much time I have. Yeah, perfect. We got this. Is the abbreviated action. And we know that there's a variational principle for it, because that was part of our derivation. So we're almost to the point where we could calculate with it. And so I'll just write finally. We just have to assume that these coordinates q, they're no longer a function of the time, right? We eliminated the time. They're a function of some parameter. And then if we find those q's through hook, by hook or by crook, then we will have the parametric equations for the trajectory. So assume now, so now let q sub I equal q sub I of lambda equals some parameter. If you were to have q of lambda for the whole problem, then that would be the parametric equations for the trajectory, right? It's not the it's not the time, it's a parameter. Then what we can do is then qi prime is equal to d qi d lambda. We're just defining that we're going to have, you know, standard derivative there. And for S0, we will have the root of 2e minus u, and remember u is a function of q, double sum, or aij's, or whatever we're calling this time, kj, also functions of q, and then the dq so that dqi is equal to qi prime d lambda. So now I've got the qi prime and the q, so the qk prime, qj prime, and I've got a d lambda squared. I got 2 d lambdas, so I pull those outside here, d lambda. And now we have something we can calculate with. Maybe I should write this in the following way. I'm going to write the same thing once more with all of the arguments for S0 is equal to integral. Just make sure we have all the arguments here. So it's 2e minus u of q. I put the q as a vector, right? Both values. Times this double sum. And I'm just going to go I and j. aij of q vector. And then we've got times qi prime, qj prime, d lambda. And the same thing holds, right? The q's are functions of lambda, the q primes are their derivatives. Okay, because what we have here, to get to the punchline, we have f of q1 to qn, q1 prime to qn prime. And when we have an object like that with a variational principle, then actually the Euler-Lagrange equations of this thing, the Euler-Lagrange equations of this thing in the red bracket are the differential equations. Okay. Euler-Lagrange equations didn't, remember when we derived them early in the semester, they didn't care if it was physics or whatever. They just had to be a function of the coordinate and its derivatives. Coordinates and their derivatives. So this is the concrete form of the principle of Mobertuise. If you can write down this thing and take its Euler-Lagrange equations, then those are the equations that'll give you the trajectory. Okay, so we're going to finish up with that thought, and next time we'll, be fresh, start with that, and move on. So, because we have a variational principle, we have the Euler-Lagrange equation for the thing. So we have d lambda, that's our parameter, partial f with respect to q sub I prime minus partial f partial q sub I is equal to 0. See, it's back to the variational calculus. Can't overstate how important the variational calculus is for this subject. So that's the idea. The q's are now functions of the parameter lambda. And what we're going to do next time, we'll review this at the top of the hour, and then we'll do a couple of interesting problems like this. And what we'll see is this will give us back the Kepler problem. And in fact, when we set this thing up for the central force Lagrangian, central force expressions, and do, you know, these equations and the other ones that hold true for this type of system, we'll actually run into the integral that we solved early in the semester. And once we run into that integral, we'll be done because we know where it leads. So that's what we're going to do next time. We've arrived at a new principle of mechanics, or it's a related principle of mechanics called the Mobertuise principle, and here it is. Okay? It's very related to what we've done, but you'll notice it's also different. Square root of these things. Okay, good. I'm going to leave it at that, and we don't have anything new to assign for this yet. Next time we'll actually take this from the top and do a couple interesting problems. Good.